And we will not get to an assignment slide today, so that all works. Okay. So a lot of times people come to this class and they have a sense of what an atom is, and we're going to kind of talk more about what an atom is. Starts with the letter N. What's in the center of an atom? Nucleus. Yep. Nucleus. Oh, but I heard, yes, neutrons. Actually, there are neutrons in the nucleus.
That's
I know.
Are we talking about like literally what's in there, or like the stuff that?
Yeah, the region or the thing is called the nucleus, and we have neutrons. Anybody know what else we have in the center of an atom?
Protons.
Very good. We also got protons. Think Captain Proton. The symbol for protons is P with a little plus in the corner because they're positively charged. And the symbol for neutrons is N with a little 0, and because they don't have any charge. That's a nucleus. Okay, so what about what's outside the nucleus? One more particle.
Electrons.
Electrons, yep. And those are, I'll put electron out here. And for electrons, a lot of times you'll kind of see it, you know, it's all kind of like, electrons are, they're out there. They form they have a lot of motion. Electrons have a lot of motion. And there you go. So those are the three main ones that we're worried about in chemistry. I have a figure coming up or later on to talk about atoms, and if the nuclei are very small, the nucleus of an atom is very small. If the nucleus of an atom was scaled up to the size of a BB, which would be a lot of scaling, then the nearest electron in general would be like, 10 stories, it'd be like 100 feet away. In all directions. So then think of a BB, think of the next closest atom. So you basically got to go, what, 200 feet away? So nuclei, and then what's in between the nuclei? Because what's outside the nucleus? The electrons, yeah.
That's when they give it, that's when they share.
What's that?
That's like when they share and take.
Yeah, exactly. The electrons are what stick atoms together. They share them, and they give them, and they take them, and they share them. Exactly. That's what keeps two atoms together. I just think that is so cool. And so the rumor is that when the guy finally figuring out kind of the structure of an atom thought about that, he's like, oh my gosh. So that means when I'm stepping on matter, which is made up of atoms, basically it's mostly empty space. It is. We are hovering. I think that is so cool. Okay, so I'm going to bring the figure in, I think, in a minute. But I think I'll just probably recreate it here. So this is seared in your mind. All matter. We've got this little logic tree. It's either a pure substance or what?
A mixture.
Very good. It's pure substance or it's a mixture. And if it is a pure substance, it can be a what or a what? Do you remember?
Heterogeneous mixture or
Two types of mixtures. There's a heterogeneous mixture and homogeneous mixture.
Pure substance is an element or a compound, right?
Yep. Yep, you're both right. Yep, and pure substance is an element or a compound. My abbreviation for compounds is CPD for compounds. So we can take elements and build them up and form compounds, but to do that we need some sort of chemical reaction. So I'll abbreviate chemical reaction, CHM122, chemical reaction. And we can also take a compound and break it down to its elements by some sort of chemical reaction. New substances are formed in both of these cases. with a chemical reaction, new substances are formed. So what this says is if you have an element right here, if somebody says, I have a chunk of matter and it's an element, then all of those atoms must be the same. Like they have, it's iron. They're all iron atoms. It's hydrogen. They're all hydrogen atoms. And all this is saying is that you cannot focus on an atom and you cannot break it down. You can't break an atom down by ordinary means. I'll go ahead and tell you what extraordinary means are. That would be nuclear chemistry. Nuclear chemistry is in extraordinary. Ordinary chemistry is, we're not changing the nuclei of any atom. So that's all that is. Okay, so here's a figure of a textbook. I think this is the figure of a textbook, sorry. This is a figure from your textbook. I think it's from your textbook of the periodic table. Sometimes students take this to class and they're like, oh my gosh, I have to memorize all those little elements? The answer is no. Okay, but we'll be talking about how each box represents a different element. You probably recognize, like C stands for carbon, yep. N stands for nitrogen, perfect. S stands for sulfur, exactly. So periodic tables have some things in common. This periodic table doesn't happen to have the names of the elements, but some periodic tables do. For this periodic table, and we'll be talking about this, do you see where it goes 1, then it goes 2, so you go across, and then you go down here 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 through 18, 19, etc. through 36. So they kind of, and we'll be talking more about that, but each time you go up in those numbers, those are the number of protons in the nucleus of an atom of that type of element. Okay, so I think that is pretty cool. So for instance, let's pick on, what does Ni stand for? Nickel, very good. How many protons in the nucleus?
28.
There's 28 protons.
I thought you just subtracted from the.
That's for the mass. You subtract
Yeah.
protons and neutrons, you subtract from each other.
Yeah,
Protons and
well,
electrons.
electrons can kind of come and go, because on that picture of the atom, we said that the electrons are outside the nucleus, and the electrons can actually kind of come and go, but the nucleus of the atom with the protons and the neutrons stays intact. Yep.
That's how I remember it.
So, do you guys already have these? Probably, yeah. You guys told me carbon is C, copper, Cu, cobalt, Co, sodium, iron, and potassium. Special K, that's how it got its name, Special K, because it's potassium enriched, I think. So a good example of, and sometimes I have to kind of break students of this, but if you have 2 letters, for instance, cobalt is 2 letters, the second letter has to be a lowercase. And the good example, if that's cobalt, what is this compound? Carbon monoxide. It is carbon monoxide. Okay? So you have to be careful and make the second letter lowercase if there's a second letter. Then I have some pictures. Now, it's hard to take a picture of an atom, in part because in order to see anything, let alone take a picture, basically you need light to reflect off of that object. And if the light wave is bigger, if I'm saying this right, yeah. If the light wave is bigger than the object you're trying to reflect off of to see it, then you're in trouble. Okay, so basically the wavelength of light waves gets too big relative to an atom. So we just can't see individual atoms. We can see a bunch of atoms together, thank goodness. Everything's atoms together and we see them. But just one by itself is really hard. So I have some slides here on kind of the elements and where they stand with regard to having a lot of that element or not much of that element. So starting with the universe, and hydrogen is the most abundant element in the universe. Nitrogen, the element nitrogen, is the most abundant in the Earth's atmosphere. Good. So as we're kind of walking around here, this is the atmosphere, the air we're breathing. It's about 80-20, 80% nitrogen, 20% oxygen. Yep. Oxygen, though, is the most abundant in the Earth's crust. So some of you might, if you're into rocks and that sort of thing, a lot of times those are oxides. So we have a lot of oxygen tied up in the Earth's crust. We have some pie charts. It makes me hungry. This is showing you kind of with a graph the relative amount of hydrogen in the universe. This is in the universe. And this is actually not by weight. This is by number of hydrogen atoms. So most of the atoms in the universe are hydrogen. I think that is so cool. And if you study astronomy, they'll kind of talk about the universe and why that is. That is so cool. So this is by weight, not by individual atoms. But again, the Earth's crust is mostly oxygen by weight. And then this one is the one that kind of freaks me out a little bit. So it's the whole taking a human body and separating it by like different elements. We have a lot of water in the human body, so that might be kind of why we see a lot of oxygen and nitrogen by mass. These are just kind of things to think about. Again, the periodic table is, it's the periodic table. And each box represents a different element, and each element has, for that atom, a different number of protons in the nucleus center of that atom. Not very many gases. We have the noble gases. I'll go ahead and tell you, because we'll be talking more about this on Monday. But the noble gases are what we call group 8A. So, let's see, is it Roman numerals over here? Yeah. So how do you do Roman numeral 8? VII, right. Sometimes I just kind of assume we're all on the track there, same track there. VII actually is over here. VIII, excuse me. This is 8A. So these are our noble gases. And what we're going to see is that as you go down the periodic table in a column, they are all a family of elements. Okay. Other elements that are gases, we have, did I talk about Hoffer-nickel in here, the diatomic elements? Okay, good. So you might recognize some Hoffer-nickel elements there, other gases. We only have 2 liquids. We have bromine is a liquid, and what's Hg the symbol for? Mercury. Yep, bromine and mercury. Anybody in here play with liquid mercury? No? Okay. No, that's old people. And most things are solids. But this makes me smile because what governs whether something's going to be a gas, a liquid, or a solid? You figure temperature, right? Temperature and pressure a little bit. Because if you want to take a solid and make it into a liquid, what do? You heat it up, yeah. So these are under normal Earth temperatures and pressures. Oh yeah, so we already talked about this a little bit. There are 7 diatomic elements. Many of them are gases. One is a liquid. So this was the Hoffer-nickel thing I talked about before. So Hoffer-nickel. So I can put little subscripts that hydrogen, oxygen, fluorine, bromine, nitrogen, iodine, and chlorine. So there are the 7 diatomic elements on the periodic table. I called these guys, oops. I called these guys the 8A. Goodness. They're 8A. You guys told me VIIIA. These guys right here, these guys are 7A, and they are called the halogens, beginning with fluorine. Okay, so I brought, you guys already have these. But if you're looking for something to do this weekend, there isn't any homework in this class. But what you could do, if you want to start getting ready for your Unit 2 exam, is to take a blank periodic table. And this is the same one that you'll get for your tests, for your Unit 2 test. You'll get one just like this. And also it's the same one that is on like the cover of your notes.
I actually think I have one from biology that we did.
So remember I said that, yeah,
I got it
very
all
good.
filled out.
Remember I said that the whole number is the number of what subatomic particle? Like for instance, what did I pick on? Let's
She
see,
said 28.
28, yeah, we picked on nickel, didn't we?
Yeah, that 28 has 28 protons.
Right, 28 is nickel, and actually we're gonna call that the atomic number. So next to atomic number, if you wanna say number protons, that's one of the things we'll be covering next week. Atomic number equals number of protons. Okay, and if you have a bare bones periodic table, by golly, it's gonna have the atomic number. So we said 28, all right, so 28 is between, obviously, 24 and 30. So all this is saying is if you find 24, so what element is 24? Chromium, very good. And what element is 30?
Zinc.
Zinc, yep. So for instance, what this is saying is you need to know just the symbol and the name. So you need to know CR is chromium, so Fe is what? Iron, yeah. So you can take, what I probably would do is just make sure I'm kind of on track with what the teacher's asking and just kind of take this and circle these. Does that make sense?
Well, I'm sorry, obviously this isn't biology, but are we gonna need to know like the 1, 2, 3, 4, 5, 6, 7, 8, 8, 8? Like across the
Maybe.
top?
They were all, oh, you mean these guys, these?
Like across, like 1, 2, like this is group 1, group 2.
Yeah, yep, we'll be talking about that later, yep. What JC is saying, and I kind of mentioned it before, remember I kind of went clear over here and I called these 8A, and you see on your black and white periodic table 8A. And then I have 7A, next to that there were the
An
halogens.
extra 7A there.
What's that?
Hydrogen, or,
Hydrogen is twice?
yeah.
Yep. And the reason is sometimes hydrogen plays like these guys. He's noticing hydrogen is twice, and hydrogen sometimes plays like these guys. So it is definitely there twice. So 92, what element is 92? Atomic number 92.
Uranium.
92 protons. Uranium, yes. That's the heaviest one you need to know. I think this is so cool. Because if you find uranium, you're like, okay, 92. There's a bunch after 92, because actually we're up to 118 now. All of those other ones, how does this work? Their half-life, they're unstable. Anything heavier than 92, 93 plus actually has been synthesized. And the word synthetic means man-made. Yeah, so 93 and above is man-made. So one of my pet peeves, especially recently since I told you we're clear up to 118, and then these actually have names. So on Monday we'll kind of look at these heavy guys here with 118 protons. One of my problems is when they say they discovered that element. I'm like, dude, you made that thing. You didn't discover it. So part of the game in making a heavier element is can you isolate it, and can you make it last long enough for it to count? So I just think that is so cool. Okay, well, that's how far I wanted to get, just to kind of get our feet wet. And then we'll pick up here on Monday. So no homework due. And let me know if you have any questions about your tests and stuff. And we do have a few minutes, 10 minutes, so I can pull up the grade book if you're not one that finds the grade book. But otherwise, you can see the grade book too to see where you're at in the class.
Can I show you this real quick?
Sure.
Yeah, this is the one that we filled out for biology. So like, I have like the valence electrons. Not really gonna need to know any
Yeah,
of that
we'll be
stuff.
talking about that.
Okay, so I can just leave this one how it is then, because it'll
Mhm.
probably
Yep.
be a lot like it.
Yep. That's very good.
I should make sure it was gonna be right.
Yep. That's neat how the sciences just kind of merge.
Yeah, we
From
talked
one
about
round.
like all this stuff we're talking about today is like a review of what we did, because this is what we did like the first week in biology. So it's like leading into each other.
Uh-huh. We'll take it.
Yeah, I will. That means I already know it. It's like a review for me.
Uh-huh. I like that feeling. Let's see if I can get this to work. Might have to call the tech people. Bye, Austin.
This is Jared.
Oh, thank you.